Welcome, everyone. Thank you for attending our session. The title of our paper is Fully Quantized Image Super Resolution Networks. The authors are Hu Wang, Peng Chen, Bohan Zhuang, and Chunhua Shen. We are from the University of Adelaide. Before we head into the details of our paper, I would like to mention several concepts of our paper, which are model quantization and super resolution, image super resolution. For image super resolution, if you have a low resolution image and you want a high resolution image out of it, then you will feed this low resolution image into SRNet, and some magic happens here, then high resolution image will be outputted. For model quantization, is totally different methods of different domain. It is a set of prevailing methods for improving the inference efficiency, which allows for replacing the expensive flow point operations with efficient bitwise arithmetics. So imagine you have a huge network, whatever the weights or the features within it are all real values and continuous values. So you can consider them, they were passed through a straight through functions, which you have a real value of x, and then you will get exactly the same x out of it. But the model quantization methods replace these functions with a quantization function. If you have an x still as a real value, and then will be quantized into several discrete values. So it enables the model to compute them into a more cheaper way with the quantization bitwise operations. So it will not only save a lot of computation powers, but also if you have a large feature maps to store, it will save the memory scaling as well. So let's get back to the image super resolution again. Image super resolution, usually they'll be applied on some edge devices. There are wide range of applications, something like smart televisions. If you want to upscale 4K videos into 8Ks, or smart cell phones, and you want, if you want to take photos, there are zoom in, zoom out operations requiring super resolutions. So it is of great practical significance to develop accurate, real-time, and energy-efficient image super resolution inference models. So that's the intuitive, that's why we combine model quantization with image super resolution. For image super resolution models, usually they'll be divided into 3 steps: feature extraction, nonlinear mapping, and SR image reconstruction. Image feature extraction model extract features from the images to a feature domain. And nonlinear mapping modules consist of a lot of nonlinear mappings, map the functions, map the features into other domain. And SR image reconstruction directly construct the image from those features. So if the model learns well, the features here should be distinctive to construct features. Some existing quantized image super resolution models only focus on the center model. But it will save a lot of computations, but there are some problems. Inevitably, there are a full precision path out there, so it will hinder the application of super resolution on edge devices greatly. So what we did here, we quantized all 3 modules as long as the skip connections. So we're dealing with large scaled and high resolution images in super resolution task. So the skip connections will store huge feature maps out there. So if we quantize the skip connections features, it will reduce the memory usage greatly as well. This table is an extension of previous slides. These existing models usually focus on the quantization of weights and feature maps, but they ignore the modules, the first and third modules and skip connections. What we did here, we quantized all 3 modules, as well as the weights, features, and also the features of skip connections. So this is a process of quantization in typical residual blocks. In the process, Q function represents the quantization function. So when X passed in to convolution layers, then BN layers quantized, and then ReLU and element-wise adding, and the Y here will be quantized to Y hat to the next module. next layer, to pass to your next layer. So which means every value passed to your next block or layers already be quantized, which means this X already been quantized by previous layers or previous residual blocks. So everything, every values within our framework has been quantized. Another thing worth to be mentioned here is the dotted products around the bin layer. In the inference time, we use the techniques of bin folding. So we fold the bin layers into preceding convolution layers to get rid of the extra flow point operations based on this formula. So the other contribution of our network is we empirically found that for different layers within our network has different ranges of quantization. For example, in the first one has the range of -10 to 10, but the other one has -100 to 100. So it's totally different. And after quantization, they'll be different as well. So how do we solve this problem? We should have automatically find the appropriate, the intervals for quantization. So we propose a distribution where interval adaptation, which is shortened as DAIA, to estimate the quantization, to estimate the interval of quantization automatically by parameterizing I. So specifically, we use a moving average of the max value within the tensor V. And this process is performed the first L iterations of the model as a warm-up. Then the parameterized interval I is optimized with gradient descent or backpropagation with the other network parameters. So it's totally optimizable. And for each quantizer, there will be a different quantization, different interval I. The other contribution we found, the other observation we found is some of the layers within our network, before and after quantization, they have totally different ranges. For example, like this one, the range from -0.3 to 0.3, but the other one is from -0.015 to 0.015. So it's totally different from the categorical distribution after quantization and before quantization. So what we did here, we proposed a self-supervised quantization aware calibration loss for each of the real value to be quantized, tackling to find optimum parameters to minimize the difference before and after quantization with the backpropagation and gradient descent. So the SQCL objective is before and after quantization. We try to drag them together and we'll try to shrink down the difference between before and after quantization. So you can see that from the right part of the figure, with SQCL objective, the categorical distribution is calibrated to fit the data distribution before quantization quite well. Eventually, the objective function for proposed fully quantized super resolution networks is the weighted sum of the super resolution loss and alpha times the quantization loss. So this is experiments of our model. We did different variants of our methods compared with the existing methods, including we tried different base levels of the weights, features, and skip connections to compare with the existing models on both ×2 scale and ×4 scale. So we can notice here, even without the center model, the nonlinear mapping model, the super resolution model can already did pretty nice, which means we should also quantize the first and third modules. Otherwise, it will greatly hinder the application of quantized super resolution models on edge devices. And you can notice here, this module, which our model with 888 bits of weights, feature maps, and skip connections can already have good results comparable with the full precision models. And we also developed another light version of it. So for the center model, we try to use less layers, and it will also have even less OPs and memories, but have comparable results with the previous methods. So this is the ablation study of each components. The experiments showed on this setting. And you can see here, we have two different modules and different components. With all the full components, our full model has the best results, but we try to get rid of each of the components, then the performance get dropped down, which means each component is effective to increase the performance of the model. So this is a visualization experiment of the model. On the time for upscaling, we did it on SR-ResNet and SR-GAN. So 888 model is already like better than, this is HR model, and this is a bicubic upscaling. Our model has better performance than the bicubic upscaling, has comparable like performance visualizations with the SR-ResNet and SR-GAN. So this is another visualization experiments of the similar results. You can see that our models has comparable results with the SR full precision models and SR GAN full precision models, but much better than the bicubic upscaling. Thank you. Thank you for attending. That's pretty much for our session.